So, this is what we implemented for, we are looking at this GMC right now. So, let me make it type 2. Okay. I will delete this. So, how do we choose the gain? So, now 0 you have placed, you need to find the proportional gain. Okay. So, where will you place the first 0? Before the or at the resonance frequency, you can put that also, it is not a problem. So, the thing here is like we have only 2 poles here. If we had one more pole, let us say 2 pole in the sense 2 real poles and 1 integrator, so 3 poles, and let us say we have one more real pole which is outside UGB. Okay. Then that pole will also contribute in the phase drop, because that is outside your UGB, but it will have some contribution, 10 degrees, 15 degrees, whatever, depending upon how far it is from your UGB. And later we will know when you talk about type 3, we have to have this intentionally we put that pole actually, because we want that gain to drop, otherwise there might be some noise issues. That is the one thing. Other thing is the output which you are feeding back, it has some ripple actually. So, we do not want that ripple to appear here. So, larger your RP is, the more ripple will appear here, okay, because that will be simply whatever the your in the feedback signal you have, that has some ripple component, that will get amplified by GM RP. Okay. So, if RP is larger, then that ripple will be higher, and in order to suppress that, what we put another cap in parallel with this or directly at the output of your compensator. So, that pole will appear at, so it will have a pole. So, where will that pole appear? If I have a cap here, let us say, let us say I call it CP. Where will it appear? 1 by RP CP, huh? By the time you hit this frequency, your capacitor CI will be shorted, huh? So, if this capacitor is a short circuit, then RP in parallel with CP, that is it. That is what you will have at high frequency. So, you have a pole at 1 over RP CP. So, once you have decided the RP, you choose this CP in such a way that it is outside your UGB, but what will happen in that case? This gain okay. It will get modified with this, and your UGB should be somewhere between what? Omega z and omega p. So, if this is your omega naught, I will say, which is omega naught is nothing but resonance frequency, then your UGB will be somewhere here. Okay. So, that your omega p is outside your UGB, but 0 is inside your UGB, and not only inside UGB, but below the resonance frequency, or in the worst case you can have at the resonance frequency, but the moment you put it out beyond the omega naught, then it may not help. Okay. So both the zeros, not just omega z which is coming from this compensator, but the second zero which we introduced by adding ESR, that should also appear at omega naught or before that. So that at omega UGB you get enough phase margin. Okay, so that capacitor will be there, we have to add that cap to suppress the ripple. If you do not do that, then you may have some noise concerns, and we will talk about that later. So now in the loop gain, if I want to find the value of these components RP, CP, CI, everything, how do I do that? So first thing you need to know where I want to place the 0. Okay. So once we place the 0, you can find the value of RP and CI. Okay. And so assumption you have to make, because there are so many unknown components here. So either you fix the GM, once you fix the GM, then CI will decide your integral gain, and 1 over RP CI will decide the 0 location. So let us say I want to put omega z equal to half of omega naught, which means half of square root 1 over LC. So what would be that? We calculated this, 0.1, half of that 0.174 divided by 2, 0.087, or pretty close to, I will say 0.9. 0.09 mega radian per second, and which is 1 over RPCI equal to okay. Now assume GM equal to 1 milli ampere per volt. Okay. So what we don't know here? So at this moment we cannot even define the CI, okay, because CI will, we have two RP and CI, two variables here. So if I define the CI, then RP can be calculated here, but how do I define CI? What will determine your UGB? The gain at 0 dB. Why Ki?
Because if Ki is very high, then will
No, but that will move your 0 also, so it will not help. We talked about that. The mid-band gain you have to adjust by simply only changing the proportional gain, which is nothing but GM RP. So GM is fixed, so we have to find the RP by finding how much gain we want at that UGB. Okay. So how much gain we require at UGB? What is the gain right now without compensator? What is the gain? So gain at UGB without compensation. How much is that? I will call it G0 UGB. How will you find that? Ku naught. So Ku naught is nothing but beta VDD over Vm omega by omega GB whole square. Okay. So KAU 0 is VDD over VM into beta. Okay, you can substitute that once you have that value, but we want to generalize this. So which means how much gain you require? So after compensation, what do we want? We want the gain at UGB equal to 1. So what is the gain after compensation? G0 UGB into what additional you are getting, additional terms? What is the DC term you are getting from compensator? Your this. GMRP? What? Anything else? Which 0? Second 0, first 0? Second 0. First 0 will cancel integrator. So that will already incorporate here by having GM into RP. Okay, that is your midband gain. Then you have a second 0. So how much gain second 0 will introduce? Omega UGB by omega Z or omega Z ESR. Okay. Substitute this and this should be equal to 1. Correct. Now substitute these values and what you get here, KU 0 omega naught or omega UGB whole square into GMRP into omega UGB over ESR equal to 1. Now I will choose omega Z ESR equal to omega naught. Okay. So this implies KU 0 and this is omega naught equal to 1. So cancels out one term and this become KU 0 which means RP equal to omega UGB over omega naught KU 0 GM. Correct. Omega UGB is known. You are designing your system and usually you design omega UGB equal to 2 pi FSW over 1/10 of your switching frequency. So switching frequency is known, you substitute that, omega naught is known, L and C component you already know, RP can be calculated from here. So once you know the gain, zero frequency you already know, correct? So Ci can be calculated from there. So once this is known, and omega z we are substituting at half of, and that we have already calculated that 0.09 equal to 1 over RPCI, and Ci is nothing but 1 over RP. Okay. So whenever you are compensating, the two things you have to remember. Your first zero is used to cancel the integrator, so that you can move as low frequency as you want, okay, because that has nothing to do with the LC. But you cannot make it very low frequency. The reason is you would require very high value of capacitor or resistor. If you are increasing the resistor, then you have to reduce the GM, but usually we already talk about if you reduce the GM too much, then you may have offset problem. So GM is already you have decided, okay, this is the GM I want to design for because of the offset. So now you have only RP to change in order to adjust the gain, okay. So if I want to move the frequency very low and gain is already adjusted, then I may require a very large cap, and on chip putting the cap will take lot of area. And there is one more problem with that. I mean, ideally I would like to keep this first zero also as close as possible to omega naught in order to reduce the value of C, and also I want a gain, my gain response to be looking like, what is the ideal gain response for your stable system? First order, if you have only integrator, first order system, and that is what you do actually. Ultimately you are trying to push everything outside your UGB or cancel anything extra in the UGB, so that leftover is only one pole, that is it, which means you try to make your system, no matter how many orders it is, looking like a first order system, that is it, so that you get a very stable response, and that is what you do here. So closer to your first order, minus 20 dB decade, very nice falling gain response, it is, you will get a best response out of that. But if you move your 0 at very low frequency, your flat gain is changing here. So this guy, if I move it here, 0 here, then it will look like, ideally I want this to keep falling to look like a first order. So your settling response may not be as good as first order in that case, okay. So that is a one thing. Other thing is I already told about that, and if you could keep this 0 at lower frequency, then ultimately you are increasing the proportional gain, and if you are increasing the proportional gain, then your UGB may move at higher frequency. So you have to adjust back. So you cannot arbitrarily make this 0 at very low frequency, and if you make this very low frequency, then what control I have to reduce the gain then? Yeah, no, what I am saying, this flat gain, okay, then you have to shape your curve like this, the whole curve has to be shifted along with integrator and your proportional everything, if you made your omega z at very low frequency. So your mid band gain required will be much lower, and that may basically degrade your transient response, because in order the output to settle, you need to have a high gain. If your gain is not high, then your response will be sluggish in that case, correct. I mean, what is the purpose of having a high bandwidth? When we say high gain bandwidth, that means your gain and bandwidth both are high. So if you look at a first order response here, in this at lower frequency, you have a very high gain, okay. But if I make this response like this, it is useless, I mean, even though you are not crossing UGB, You are maybe crossing your EGB here, but what happens the gain here? The gain is very bad. So your response won't be good in that case. Okay. So that's why we want to move this 0 very close to omega naught, so that you cancel the integrator before the resonance appears, and then you have a second 0 to cancel one of the resonance poles, you get enough phase margin. So your gain and phase response both looks very nice. It's like you're more closer to first order system.